Hello and welcome to another video. In this video we're going to be working on out of boundary paths. And in the problem you have an n by n grid with a ball, and the ball is at some position, and you're allowed to move the ball to one of the four adjacent cells in the grid, possibly out of the grid, crossing the grid boundary. You can apply at most max move to the ball, return the 5 integers, or given the 5 integers, mn, max move, start row, and start column, return the number of paths to move the ball out of the grid boundary. Since the number is very large, return it modulo 10n plus 7. So this m by n is like kind of pretty easy to figure out because essentially we're just given some like rows and columns for a grid. So that part's pretty straightforward. And then they just give you like a start row and start column for the ball, and you want to figure out how many ways you can kick it out of the grid. And at first in this problem, I actually tried to do a BFS, but then I realized you have a lot of repeated work. So normally a BFS is really good for like, what's the fastest way to get somewhere? So like if you have the ball start at some location and you're trying to get to some other location, a BFS would work for that. But if you have BFS doesn't work great if you can repeatedly go to the same place, and in this case you can. So for example, let's say we start here, like what if we move here and then back here? So that should be allowed because the number of ways to get rid of the ball out of a row and a column doesn't only depend on the row and the column you're in. It depends on the row. Let's make this bigger. It depends on the row, the column, and the moves left. And I'll show that later, but let's go through these examples. So in this first example, you have the ball here, and they show you like how many ways you can kick the ball out. So one of the ways is right where you are, you can just kick it out this way or this way. So that's 2 moves. So this is 1, 2. Now there's other things you can do. So you can kick the ball down, and then once you kick the ball down, you can kick it out left, or you can kick it out right. So that's 3 and 4. You have 2 moves total. And then the other thing is kind of similar. Instead of down and left and down, you move it right and then up and right. So 5 and 6. And in the second example, you have, let's see here, you have 3 moves total. So one of the ways is you can kick it up or down. So that's just going to be 2 moves, right? Then another way is we can, or it's not going to be 2 moves, but this is going to be like 2 ways to kick it out. Another way is going to be to kick it left and then get rid of all these 3 locations. So this gives you 3 moves. Same thing for the right, kick it right, and then 3 locations. Now another thing, and this is why it's important to let the ball go back, you can also kick it left and then back and then up or down. So this is 2 moves, right? So even though it was in the same location before going out of bounds, these count as different things. And that's what you have to recognize with the picture. And then the same thing, right? So there's 2 here. So we have 2, 3, 3, 2, 2, which is 12. So let's just kind of draw a grid and show why we have a lot of repeated work. So let's say we're at like this location for the ball. Like here's the ball. Let's draw it. And let's say we have like 6 moves or something. So let's just look at some easy place we can get to. Like let's say we can get to, like let's say we're trying to figure out like how many different ways can we get here that is the same thing. So you can go here and then here, or you can go here and then here. These would both lead you to this location with 4 moves left. And so from here, from this spot, there should be the same number of ways to kick the ball out, right? And that's why, like I said, it depends on the row and the column and the number of moves left. Because if we're here with 1 move left, we can't get rid of it. But if we have like 50 moves left, we can get rid of it in like all kinds of different ways. So that's kind of the idea. You want to solve one time how many different ways can you kick the ball out given row, column, and moves left. And then from there, once you solve that, like let's say we do get it here with 4 moves left, then whenever it comes here again from some other location, like let's say we go here and we have 4 moves left, we solve for this, how many different ways can we kick it out with 4 moves left. And then when we come in maybe like this way, we can solve for that again. So it's essentially problems and subproblems, which are just going to be DP instead of BFS. And yeah, BFS is good when you don't revisit a cell or you have some like limited number of moves. And even though you do have a limited number of moves here, the problem is you're going to have so many repeated states, you're still going to go too big. So that's why DP is going to be better, because you're doing recomputation, right? You are visiting the same place multiple times and then you want to just save that once. That's why you know it's going to be DP instead of a BFS. So let's go through the DP solution for this, kind of like what we need, and then, yeah. So for DP, as always, you need three things. You need state, base case, recursive. So the state is kind of what I said before, and the nice thing is the constraints are kind of small here, so you can have a lot of things. So if we actually scroll up here, you can see M and N are 50, and max moves is 50. So if you have all three of these, it'll be like 50 times 50 times 50, which is fine. Right, which is like 75,000, which will easily pass. So that's going to be the state. The state is going to be the row, column, and the moves left, or whatever way you can either record moves left or moves taken and so on. So maybe we'll do it like this way: moves taken. Actually, let's just do moves left. Let's do moves left. Okay. So the base case is kind of obvious as well. So base case, one of the base cases is out of bounds, right? Like let's say our ball is actually out of bounds. What do we want to return? Well, we are trying to get the sum of all the different ways our ball can go out of bounds. So if we're out of bounds, we just want to return 1 here, right? Because that is one way to get out of bounds. And then the other obvious one is no more moves left. Then we return 0 because we can't get out of bounds. Like let's say we're here with no moves left, we can't get it out of bounds because we have no more moves left for the ball. Now the recursive case should be pretty straightforward as well. Essentially, wherever you are, so let's say we're here, the number of ways to kick the ball out of bounds is, well, you can either go up or down or left or right, and that takes a move. So you basically just recurse in every direction and you add 1 move to your move taken and you add up all of those. So for example, for some easy example, let's say we go back to this. Let's just say we have some small array. So let's say we have something like this. And let's just get rid of some stuff. So let's say we have something like this. Our ball is here. And we have, let's say, 2 moves. So if we have 2 moves, so one of our recursions will be here. That will return 1. One of our recursions will be here, right? So this will return 1. This will return 1. Then one of our recursions will come over here. And from here, in this one, there's 1 here, 1 here, and 1 here, right? So starting from this state with 1 move left. So let's say we start here with 2. We recurse over here with 1 move left. So here with 1 move can give us 1, 1, or go back, and then we can't get out. Now the other recursion will go right. So we'll come here with 1 move left. So we'll have 1, 1, 1. And so the total number of moves starting at this location is going to be 8, right? Because we can go up, we can go down, we can go left, and then out of bounds everywhere, and we can go right and then out of bounds everywhere. So this should be 8, I'm pretty sure. I'll just make sure this wasn't like a previous problem with the exact same thing. No, so this had 3 moves instead of 2. So hopefully that makes sense now. We're basically just recursing in every single direction, and then if we're out of bounds, we return 1. If we're not, we just recurse again, and we keep doing that, and then we can cache all this to make sure that this passes. And yeah, that's basically the idea. So the recursive case is just going to be add up all recursions so add up recursion for going left, up, right, down. So we basically just change the row and the column appropriately for left, right, up, down, and we add 1 to the number of moves we have or number of moves left or whatever you want. I'm just going to initialize moves left with our current moves. So let's say we have 3 moves. I'll just call this with like 3, and then whenever our moves is 0, that's when we'll say we can't get anything else. And yeah, that's pretty much it. So now we can code it up. So we can just do a DP function, and like I did in the previous problem, instead of making cache, you can actually just use this @cache decorator, and this will cache the results for you instead of making a cache. Or you could make a cache, either way is fine. So we're gonna have a DP function. It's going to take a row, a column, and a moves left. And I'm also going to make a directions array in the top, and I'll show you why this is useful. So directions is just going to be like this. So this is going to represent going down. This will represent going right. Then this will represent going up. and this will represent going left, I believe. Yeah, it should be fine. Okay, so typical directions array, you're basically, like if you have a row and a column, let's say your row is 5 and your column is 6. So basically what we're going to do is we're going to take the left number and add it to the row, and the right number and add it to the column. We're going to loop through all those. So for example, if we have this 1, 0, our row will be 6, our column will be 6. So this just symbolizes going down. So each one of these arrays symbolizes going in one direction, and it's very useful. So let's write down our base cases first. So if we are out of bounds, we want to return 1, right? So if row is less than 0, or row is equal to m, which is the number of rows, or column is less than 0, or column is equal to n, which is the number of columns, we want to return 1, right? We made it out of bounds. And like we don't have to check. The nice thing about this @cache decorator, we don't have to check if we have our value cached anymore. Like if we call a value that was cached before, it will automatically return. So we don't have to add things to the cache or return things that are cached. It will do it for us. Okay, so this is the case where we're out of bounds. Now we need the case where we have no more moves left. So if moves left equals 0, we want to return 0. Because we're not out of bounds, we check for that first. You want to check for that first because you might have 0 moves left, but you might be out of bounds, so this takes priority. And if we have no more moves left, return 0. So now basically we got to go in every direction and add all of that. So we can just say result equals 0, and for, we can loop through these directions. So we can say like for x, y in directions, result plus equals dp of row plus x and column plus y. And every time you move somewhere, you have one less move left, right? So it's just going to be moves left minus 1. So that's why this is convenient. You don't have to write this a bunch of times. Like you can just loop through all of your directions, and you can just add the appropriate x and y value from the array. And finally, we just return this. So return result. And then we need to call this function. So we need to return dp on. So we start at start row. We start at start column. So start row, start column, and the number of moves left is max move. So there we go. Let's see what happens. Okay, looks good. Apparently not. Oh, so we forgot one more thing. So they do tell you that this can be too big, so you want to return it modulo this thing. So we're going to store this value. And then we can do it one of two ways. We can either mod it at every single time, or we can mod at the end. We'll just mod at the end. All right. And there you go. So you can see it's pretty good, pretty efficient. You can, I'll briefly talk about it once again, kind of like previous problems, you can get rid of a dimension here. Since this is 3-dimensional, you can space optimize it and get rid of a dimension, and think about like what dimension you can get rid of. So you can technically get rid of, I'd like to think you can get rid of any of them, because basically all of these go up or down 1, but the easiest one is going to be this moves left, right? They're all about the same, they're all about 50. But moves left is going to be the best one because it's going to be the easiest. So basically, every moves left relies on moves left minus 1. So we can start at like 0 moves left and then compute backwards in a 2D array up to this moves. So you would basically get a 2D, or you'd have like a nested for loop where it would go row, column, and moves left. And at every single move left, you would create a 2D array of row, column, fill it out based on the previous one. So you would store 2D arrays at a time, and you would get rid of this dimension in space. So you can do that if you want to. I'm not going to do that. I don't think it's like super useful, and I've shown how to do that a bunch in other videos. So, and I will link how to do it, like a deep explanation of bottom-up DP if you want to do it. But I think this is good enough for this. So let's go through the time and space here. So essentially, the way to calculate time and space for DP is basically how many states can you get to, like realistically. So in this situation, all of these states, you can't always get to them, but worst case scenario you can, right? So like, yeah, worst case scenario, like let's say your moves left is 50. Well, no, it's still not going to get to all of them because, yeah, it's still not going to get to all of them. So it's not going to be quite this bad realistically, but that's just like the syntax for it. Because if you think about it, if you have like a 50 by 50, you're not going to be able to get to every cell. Like, right, if this is the max value and this is the max value and this is 50, you're not going to be able to do that. And we can show that with a smaller example. So let's say you have a 4x4 and you have 4 moves left, right? Kind of the same situation. You're not going to be able to get to every cell if you start on some. You will be able to get there if you start on some indices, I think. Like if you start on somewhere in the middle, like let's say we start here, we should be able to get to every cell. Yeah, but you can't get to every cell with every number of moves left. So you're still not going to get to like for example, you can't get here with like let's say you have 4 moves left here. You can't get here with like 3 moves left, right? So it's not quite going to fill this up. So in reality, it will be less than this, but as far as big O complexity, typically what you do is it's all of your dimensions multiplied by each other. So we have row times column times moves left. And then you want to figure out like what you're doing in your DP. Is your DP constant time? Do you have a for loop or anything? So this is constant time, this is constant time, and this is also constant time because even though we have a for loop, we only have 4 directions, so that's constant time. So this inner part of the DP is constant time. The outside part is this, and that's basically the time. And the space is going to be the exact same thing because we're storing a cache. So like I said, if you did want to space optimize it, you can get it down to this if you wanted to. But I'm not going to do that here. I think this is good enough. So yeah. I think that's going to be all for this one. So hopefully you liked this one. And if you have any questions, as always, write in the comments. And if you did like the video, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.